In this video, we're still in Chapter 14, Part B. We're going to talk about some acid-base reactions. Of course, one of the most important reactions of acid and base is neutralization. When an acid and a base are mixed, the hydrogen from the acid combines with the hydroxide from the base to form water. It generally looks like this. Acid plus a base produces water plus a salt. These kinds of reactions are generally called neutralization reaction. The net ionic equation for this reaction is that basically the hydrogen ions react with hydroxide to form water. Here's another example of a reaction of an acid with base. Generally carbonates, CO3 minus 2, or bicarbonates, HCO3 minus 1, they react with acid to produce water, gaseous carbon dioxide, and a salt. It's called a gas evolution reaction. Here's the reaction. Acid plus sodium bicarbonate produces water and carbon dioxide plus sodium chloride salt. You're familiar with the fizz that we very often see. Acids react with metals in a way to cause metals to go in the solution. The reaction between an acid and metal usually produces hydrogen gas and a dissolved salt containing a metal ion. For example, the reaction of hydrochloric acid with magnesium produces hydrogen gas plus a solution of magnesium chloride. Acids dissolve many metals. Here's the example of an acid dissolving the magnesium that we just looked at. Sulfuric acid will dissolve zinc to produce hydrogen gas and the aqueous solution of the salt. Even iron will dissolve in hydrochloric acid. Some metals do not readily act with acids, for instance gold and silver. So if the bars that imprisoned James Bond were made of gold, a pin filled with hydrochloric acid just wouldn't dissolve the bars, and James Bond would never have escaped. Reaction of bases. Well, again, they partake in neutralization reactions. Other kinds of base reactions are the reaction of sodium hydroxide with aluminum and water. Important reaction that's used in the recycling of aluminum. Sodium hydroxide reacts with aluminum to form a compound, sodium aluminum hydroxide plus 3 hydrogen. Aluminum is one of the few metals that dissolves in a base, and so if your household plumbing pipes are made of aluminum, it wouldn't be safe to use sodium chloride, the main ingredient of product used to unclog your drains. Fortunately, use of aluminum pipe is forbidden by most building codes. Let's talk about an acid-base titration. This is a way to quantify the amount of acid or base in a solution. The solution stoichiometric can be applied to a common laboratory procedure called titration. In a titration, a substance in solution of known concentration is reacted with another substance of unknown concentration. In the acid-base reaction between hydrochloric acid and sodium hydroxide, the net ionic equation is the hydrogens from the acid and the hydroxide and the base form water. Here's a representation that might be well to look at. In titrating the sample, and the sample will be down here, the sample down here is an unknown acid. These are representing hydrogen ions. We slowly add a solution of known concentration. Here is the solution of known concentration containing hydroxide ions. And you can see what happens when this molecule adds to the unknown. You get it reacting with one hydrogen ion to form water. In this solution, it is still acid. This is acid, it's still net acid even though you've neutralized part of the acid. Suddenly, when you reach a point called the equivalence point, where the moles of the known are equal to the moles of the unknown, you have no acid or base. And so in this solution, we have only water. All the hydrogen has reacted with exactly the right amount of hydroxide. So therefore, this is neutral. And so we can follow this reaction by measuring its pH. Here's another look at it. We add an indicator, and the indicator is phenolphthalein. It is colorless in acid, and it's pink in neutral to base. So what you see is here's your unknown acid. You're adding your hydroxide. When it drops, there's momentarily a pink color form until it dissolves or till it reacts. And finally, when you get to the end point, the whole solution turns pink, and that indicates what volume of known you had to take to neutralize exactly the unknown acid. The calculations go like this. Suppose we have 10 milliliters of hydrochloric acid, unknown concentration. We do know its volume. And when we titrated, it required 12.4 milliliters of 0.1 molar sodium hydroxide to reach the equivalence point. What is the concentration of the unknown? So you're given the volume of the unknown acid, but not its concentration. You're given the volume of base to reach the equivalence point and its concentration. So you'll be able to figure the moles. First, you must write the balanced equation. Here it is. HCl plus sodium hydroxide forms water in that. And the solution map has two parts. You start with the milliliters of sodium hydroxide required to reach the equivalence point. Convert those milliliters to liters. Using the liters and the concentration, 0.1 molar, 0.1 mole per liter, convert that to moles. Looking at the equation, you see that there's 1 mole of HCl to 1 of sodium hydroxide. So convert the moles of sodium hydroxide to moles of HCl. Then, once you have the moles of HCl, you can use this information and the volume to calculate the molarity. The molarity is simply the moles of HCl over the volume of the solution. Again, here's the setup. The milliliters of sodium hydroxide converted to liters, converted to moles, converted to moles of HCl. The molarity finally then is 1.25 times 10 to minus 3 moles of HCl in 0.0100 liters. That was the 10 milliliters originally. And we got 0.125 molar is the concentration of the unknown HCl. Strong acids and weak acids and bases. Strong acids, hydrochloric acid and hydrofluoric acid, they look kind of similar, but there is an important difference between these two. HCl, hydrochloric acid, is a strong acid, one that completely ionizes, and hydrofluoric acid is a weak acid, one that does not completely ionize. Here's the way we might look at it pictorially. HCl plus water, the arrow is completely in the ions. Basically, all of the hydrogen has combined with the water and all the chloride ions are there. Conductivity, pure water is not a good conductor. We are warned often about dangers of using electrical devices when you're sitting in the bathtub, and the reason for that is because the water in the bathtub is not pure water, has stuff dissolved in it, so it's a good conductor of electricity. Conductivity of a strong electrolyte. Here's pure water. You can see the light bulb doesn't light, therefore the electricity doesn't conduct between the two. But we put a hydrochloric acid solution and we have the ions present to have a strong, bright light, a good conductor. We take a look at the conductivity experiment of a weak electrolyte. Of course, we have water, which is a non-conductor, pure water, no light. Now we have a hydrofluoric acid, a weak acid, a weak electrolyte. Only a few ions help conduct it, so therefore you get a very dim light. Some common weak acids are hydrofluoric, acetic acid, formic acid, sulfurous acid, carbonic acid, phosphoric acid. We often ask yourself, what is the hydronium ion concentration of each solution? If you have 1.5 molar hydrochloric acid, that is moles per liter, and it breaks up completely into ions, you get 1.5 moles of hydrogen ions or hydronium ions and chloride ions. So it completely ionized, the concentration of a hydronium ion will be 1.5 molar. Now you have 3.0 molar acetic acid, a weak acid. It doesn't break up entirely. So since it's a weak acid, we know it only partially ionizes. The calculation of the exact concentration is beyond the scope of this text, but we will know that the concentration of the hydronium ion will be less than 3 molar because some of it doesn't break up. Strong and weak acids, and we look at strong bases. Strong bases are one that completely breaks up dissociation solution. These are lithium hydroxide, sodium hydroxide, potassium hydroxide, strontium hydroxide, calcium hydroxide, and barium hydroxide. Unlike the diprotic gases, which ionize in 2 steps, you get complete breakup of the bases in 1 step. So calcium hydroxide, when it breaks up, produces 1 calcium plus 2 ion and 2 hydroxide ions, minus 1 each. Here's the strong base sodium hydroxide. There's the sodium, oxygen, and hydrogen. When it's dissolved, you get all total breakup of sodium ions and hydroxide ions. Ammonia, NH3, is a weak base. When it dissolves in water, here you see the ammonia molecule, NH3, it partially ionizes to form ammonium, NH4+, here's that ion, and a hydroxide ion, because it took the proton from water, but yet you have 3 ammonia molecules unionized. So therefore it is a weak base, producing a few hydroxide ions. You might ask yourself, what's the concentration of hydroxide ions in each of the following solutions? 2.25 molar potassium hydroxide? Well, it's a strong base, so it breaks up completely, and so you have 2.25 molar hydroxide ions. What about 0.35 molar methylamine, which is a weak base? Well, you really don't know because it's only partially ionized. We can't calculate an exact concentration with our knowledge, but we know for sure it will be less than 0.35 moles of hydroxide. So in the reactions, most important probably is neutralization, and we use this titration method much to determine the concentration of known acid or base. So since you can titrate, that is, add base of known concentration to an acid of unknown, or vice versa, you can monitor what volume the added base is that is needed, and you have the unknown pass through from the neutral point, which is the equivalence point, and in this neutralization stoichiometry in axis, you can then tell what's the concentration of the unknown.